Last episode, I opened up by saying I sell the best corn and soybean lineup for Southern Illinois. I believe this 100% because I picked every hybrid personally. So, a logical question you may have is why am I so focused on soils then? Dr. William Albrecht, in my opinion, the first true soil scientist and someone who progressed agriculture more than any other person in history, he used to say, when a bull and a cow get together, the cow has to do her part too, not just the bull. He was referring to the biology of the soil, but I look at it in a similar but slightly different way. When a seed and the soil get together, the soil has to do its part too. The better balanced our soils are, the more efficient use we have of our fertility and microbes. And that allows my genetics to shine. I don't believe one can work without the other. And the more we allow the genetics to shine, the bigger advantage I have on your farm, and the greater your return on investment will be. Last week, we outlined what soils consist of the sand, silt, and clay. We learned that the greater your surface area you have from things like clay or organic matter, the higher your holding capacity or cation exchange capacity is. Why is it called cation exchange capacity? If we remember back to chemistry classes in high school, a cation is a positively charged element. An anion is the term used for the negatively charged elements. Opposite charges, such as the positive, the negative, they're going to attract to each other, while like charges, positive to positive, negative to negative, will repel each other. You can visualize magnets and how they react with the push pull based on a charge when you start to put them together. Oils are going to follow those same rules for attracting or repelling each other. The term cation exchange capacity is because our soils are negatively charged. So this number is telling us how many cations, the positively charged ones, can bind to the soils, the negatively charged. While CEC numbers can vary greatly based on levels of sand, silt, or clay, there's very little we can do to change it in the short run. We can increase things like organic matter, but that can't be done easily or quickly. So, to reiterate, just in case I'm moving too quickly, positive charged ions will naturally attract to your negative soils. Some of the most common cations, they're going to include your calcium, magnesium, potassium, ammonium, hydrogen, sodium, copper, zinc, and manganese. All of these cations will stick to the soil equally. The greater the positive charge, the easier it is for them to bind to the soils. A plus 2 charge will stick to the soil stronger than a plus 1. Or a different way to look at it, and one that's easier for me to visualize, a plus 1 charge doesn't have a strong enough ability to bond to the soil where it can kick off a plus 2 charge. Some negative charges include nitrate, your sulfates, and phosphates. Your nitrates and sulfates are subject to leaching. For some reason, phosphates don't seem to be as prone to leaching, and I'm not quite sure I completely understand why. I know it has a strong negative 3 charge, but I believe it's binding more to the calcium in the soil, which I know it likes to do, than to the actual soil itself. But we're going to dive into individual elements as we progress about the series, so just be on a lookout for that. The greater your CEC, the more places there are for your cations to stick to or bind to the soil at. There is a direct amount able to be bound with each CEC. So a soil with 10 CEC can hold exactly double what a 5 CEC soil can hold. But that same 10 soil can only hold half of what a field that has a 20 CEC has. The negative charge of the soil will attract positive ions until there are no more blank spaces in the soil. Your soil will never have a bare spot. The unfilled spaces, for lack of a better word, are going to be filled with hydrogen atoms. And hydrogen will fill those sites when you run out of your cations in your soil. So instead of having your blank spaces, just imagine you're going to fill them with hydrogen. Determining your pH is just equal to the negative logarithm of the active hydrogen concentration. And that's just the textbook definition I kind of felt like I should throw in. but it's not something that's that crucial or something we need to waste time trying to learn how to calculate or truly understand. Now that we understand what cation exchange capacity is, and what cations are, and how they bind to your soil, now it is time to use these basic principles to line out our soil. Each exchange capacity has a measurable amount that it can hold. At 100% saturation, one CEC can hold either 400 pounds of calcium, 240 pounds of magnesium, 790 pounds of potassium, 20 pounds of hydrogen. And the measurement of these four or make up the core of your base saturation. Why base saturation is extremely important is going to be discussed in detail in next week's episode. One example to close out this week. A field, the same one that has the 10 CEC soil, it can hold 4,000 pounds of calcium. I took that by the 10 CEC times the 400 pounds of calcium that can be held on each CEC. If it were to have 4,000 pounds of calcium, the base saturation would read 100% calcium with little to no room for anything else. Sometimes these tests, they can get tricky if you're oversaturated with calcium, but we're not going to dive into that for the example. A 100% calcium reading would be a bad thing. But if we took that same field and we're trying to figure out what amount of calcium is required to get a calcium percentage of 68, then we're going to take our 0.68 times the 4,000 pounds, and we're going to get 2,720 pounds of calcium. Then we're going to take the same field and try to figure it out for magnesium. So for this example, we're going to shoot for 12% magnesium. 10 CEC times the 240 pounds of magnesium per CEC times 0.12 for the 12%. And that's going to give us the goal of 288 pounds of magnesium for this field. With those numbers in place, we can accurately calculate how much lime or magnesium we need to add or subtract. As you can tell, as you create and work through examples on your own farm, the higher the CEC, the greater amounts you're going to need to change your percentage. But the slower your plant and fertility will have to adjust when you need to make new changes after that. If you're wondering why I chose 68 and 12 for my percentages, that's what next week's video will be about. I couldn't explain base saturation without making sure we had the foundation of terms like cation exchange capacity and what they are. Thank you for your time, and if you stuck around this long, next week is where we're really going to dive in on ways to improve your soil with my favorite topic, base saturation. Thank you.